Welcome to this explainer. Today, we're diving into something really fascinating. We're going to trace the journey from completely abstract, invisible mathematical concepts all the way to the physical, three-dimensional building blocks that actually construct the world around us. So if you're curious about how simple ideas stack up to create some pretty complex realities, you are definitely in the right place. Let's get into it. It all really kicks off with one simple but honestly profound question. How do we actually turn abstract numbers into the physical world? Think about it from the perspective of an early learner. How do we bridge that massive gap between some invisible number floating on a page and a tangible physical reality that a kid can literally reach out and touch? Well, as you'll see, it requires a very specific progression.
All right, Section 1, Foundations of Number Sense.
Okay, so we have addition, subtraction, counting up to 100, and place value. These four pillars are the absolute essential starting points. The source materials make it incredibly clear that these arithmetic skills build early number sense. Without a solid grip on how amounts work together or why place value matters, trying to tackle spatial reasoning is basically impossible. It all has to start right here.
Moving right along to Section 2, Exploring Flat 2D Shapes.
Say hello to our very first geometric building blocks: circles, squares, and triangles. Now, in the two-dimensional world, everything is completely flat, but recognizing these basic shapes isn't just about naming drawings on a piece of paper. These are actually preliminary cognitive tools that we use to categorize our entire visual environment. The curriculum uses these exact shapes to really kickstart that journey into spatial reasoning. And the really crucial insight here is how this is taught. As the source notes, we can explore the properties of 2D shapes through creative digital drawing exercises. You don't just passively stare at a square, right? You interact with it. By tracing and manipulating these shapes digitally, learners are actively exploring 2D geometry and bringing those flat objects to life in their mind's eye.
Now for the major aha moment. Section 3, Adding Depth with 3D.
This perfectly illustrates the leap between the two worlds. With 2D shapes, we are strictly limited to length and width. But the second we introduce 3D shapes, we add a crucial third dimension: depth. That one single addition literally changes the entire paradigm. We're not dealing with flat drawings anymore. We are dealing with actual, solid objects. So to really anchor this concept, 3D shapes are defined academically by three physical features: faces, edges, and vertices. The faces are those flat surfaces, the edges are the straight lines where two faces meet up, and the vertices, well, those are just the corners. Grasping these properties is exactly how we learn to deconstruct the physical objects we encounter every single day. Imagine starting with just a standard flat 2D square. That's step 1. Now for step 2, imagine grabbing that square and pulling it outward, stretching it right into space to add depth. Boom. Step 3, that flat square has transformed into a full, solid 3D cube. Visualizing it step by step like this is such a powerful way to see that a complex shape, like a cube, is really just a flat square with depth added to it. And you know, the logic is identical across other geometries too. Take a flat 2D circle for step 1, stretch it outward to add depth for step 2, and by step 3, it expands into a full 3D cylinder. It's so cool because visualizing this reinforces exactly how our three-dimensional world is literally constructed from those much simpler two-dimensional foundations.
Which brings us to Section 4, Real-World Math Connections.
The sources outline this fantastic, hands-on activity called DIY 3D models. The whole point is to identify these geometric counterparts in everyday, regular items. So, a pair of dice? That's your cube. A standard can of soup is a cylinder. And that book sitting on your desk? That's a rectangular prism. It's a direct mapping that takes academic math straight out of the textbook and roots it firmly in relatable reality. To quote the source material directly, these shapes are the building blocks of everything around us. When someone realizes that a soup can is actually a cylinder, they aren't just doing classroom math anymore. They are literally decoding the structure of their environment. They're seeing that math and spatial reasoning are the invisible blueprints for everything we see, touch, and interact with. So, I want to put your spatial reasoning to the test right now. Look closely at the device you're using to watch this explainer. What 3D shape is it? Think about its faces, its edges, and its vertices. Is it a thin rectangular prism? Does it have some curved cylindrical elements on the sides? Taking abstract math and applying it to your immediate physical world is what true understanding is all about. Once you start seeing the geometry hiding in plain sight, you'll never look at a simple room the same way again. Thanks for watching.